Hello and welcome to this online training course. We'll start with a few advanced notions on the use of CBA-32P and Cbawin, produced by Zensol Automation in collaboration with Hydro-Quebec. Objectives of this module. By the end of this module, you'll be able to record and view any signal present in high-voltage substations, with the exception of vibroacoustic and electromagnetic signals. If you understand and learn what we show you in this presentation, you'll be able to record and view any signal that exists in high-voltage substations. The only signals you won't be able to record with the CBA-32P are those of a vibroacoustic or electromagnetic nature. If you'd like to see this type of signal, we recommend our new families of instruments such as the TAP4 and CBV. To take full control of the CBA-32P and make it do what you want, you need to know its internal architecture and be familiar with the green buttons in the Cbawin software. After a brief reminder of some of the most important elements of Cbawin, we'll show you what's behind each CBA-32P input in a simplified, easy-to-understand way. This information is essential to understanding the CBA-32P modular solution as a whole, so you can then imagine how you might complete the electrical circuits with the circuit breaker or its control cabinet. The only electrical knowledge required is Ohm's law. A good knowledge of Microsoft Windows, Word, and Excel is a plus and will give you a considerable advantage in handling the results generated by the synchronization tests. Why is it so important to understand these figures? Before going any further, let's return to the famous software numbers we talked about in Module 3. You already know that each physical input is associated with a software number. For example, the displacement recorded on analog input 3 is a real physical signal. If you analyze this signal carefully, you can know the exact position of the moving contact at all times. This information allows you to calculate the speed of the moving contact at any given moment. By plotting all these values calculated at each instant, we obtain a new curve as a function of time. This mathematically calculated curve is called a virtual signal, which we need to visualize like any other synchronization signal. Cbawin actually has 14 virtual signals, which are shown on this slide. The most popular virtual signal is number 9, which is the instantaneous speed signal of the displacement signal recorded on analog input number 3. By extension, a displacement signal recorded on analog channel 4 will be visible on channel 10, 5 on virtual signal 11, and so on. Similarly, the instantaneous speed of the displacement signal recorded on the digital optical encoder input 89 will be visible on the virtual signal 95. This slide shows a summary table of everything you need to know about software numbers for each type of input. This table is also available in your job aid and in the quick installation guide. There's no need to memorize these numbers, as they are circled on the front panel of the CBA-32P. You just need to understand the principle. Let's analyze the figures together. On the CBA-32P front panel, the first input measures contacts C1 and C2, which for Cbawin correspond to signals 17 and 18. The second input measures contacts C3 and C4, that is signals 19 and 20, and so on. For analog inputs, the first is signal 3, the second is signal 4, and the last is signal 8. In the case of optical encoders, the first is a physical signal of 89, the second 90, and so on. For commands, the current measured during the closing command is number 1, while number 2 represents the opening current. Signal 61 displays the close command, while signal 62 displays the open command. To view any signal, simply enter its number in the tables accessible via the 7th red button. This red button is the design button for graphic reports. The signals are presented from bottom to top, so if you want to see the closing current at the bottom, insert the one first on the far left. If you want to see the same current at the top, simply enter it last in the list of special signals. How to set test duration using green button number 1. To set the duration of a circuit breaker closing or opening test, you need to know the approximate duration of the desired recording. By clicking on the first green button, simply fill in the test duration field in microseconds, milliseconds, seconds, or minutes. If, for example, although not common, we want to perform a test lasting 1 minute 30 seconds, we'll enter 1 in the minutes box and 30 in the seconds box. For a test lasting 300 milliseconds and 85 microseconds, we'll enter 300 in the milliseconds box and 85 in the microseconds box. For your information, 1 millisecond is equivalent to dividing 1 second 1,000 times, 10 exponent 3. 1 microsecond is equivalent to dividing 1 second by 1 million, 10 exponent 6. This test duration time is then shown on the x-axis, or the time axis of your graphs. It appears in milliseconds at the bottom right of your screen. Then turn your attention to the interval field and memory usage. CBA-Win informs you through disavowal of its physical limitations in carrying out what you ask it to do. Note that the longer the test duration and the shorter the interval, that is the sampling time, the greater the demand on memory. So we have to be careful with these limits. When the memory bar turns red, CBA-Win warns you that your CBA-32P storage limit has been exceeded. How to set the sampling time for a test using green button number 1. This parameter, which is good to understand but not recommended for beginners, is the sampling time. This simply represents the time interval between 2 readings of a signal. This value, typically between 100 and 300 microseconds for closing and opening tests, actually represents the precision and level of detail you want to see in your signals. By analogy, a photo taken with a cell phone will be of lower quality than one taken with a professional camera. This slide shows the recording of a 450 millisecond FO operation of a circuit breaker simulator. This recording was made with a time interval of 100 microseconds. The test lasted 450 milliseconds, so the CBA-32P took 4,500 readings with a time interval of 100 microseconds between each measurement for each of the signals recorded. Note the level of signal detail. You can see every detail of the bouncing of the contact relays, the overtravel, the little noises on the currents. In contrast, this slide shows another recording of the same 450 millisecond close-open operation from the same circuit breaker simulator. The recording you see here was made with a sampling time of 32,000 microseconds, whereas the previous one was made at 100 microseconds. Note the complete distortion of the signal. We can't see nothing. It's as if the photo of the recorded signals were a very poor quality photo. The difference between a good quality recording and a poor quality recording is simply the time interval between signal readings. For the same test duration set at 450 milliseconds, only 15 readings were taken in this example. What's behind a contact input? As we saw in Module 2, the most general circuit breaker is symbolized by a main contact in parallel with a pre-insertion contact. The CBA-32P's internal contact input circuit is symbolized by a lamp and a 40-volt DC battery. To see the contact status on the graphs, simply ask CBAIN to file the signal using its software number. This example shows contacts C1 and C2, which are displayed as numbers 17 and 18, respectively. Behind the 3-pin female connector of the front panel contact inputs, there are, in fact, 2 independent circuits linked by a common point. The 3-pin contact cable completes the circuit between the CBA-32P and the T-type circuit breaker in this example. If the lamp is off, we can only deduce that the circuit breaker is open and the graph shows a 0 state. If the lamp is brightly lit, we can only deduce that the circuit breaker is closed, and the graph shows a status of 1. If the lamp is half lit, we can only deduce that the circuit breaker is in a resistive state, and the graph then shows a half state. Finally, it's easy to know exactly when the circuit breaker changes state, and we can then analyze the evolution of the contacts in relation to each other. It's this comparison exercise that's at the height of synchronization. It is important to know that the CBA-32P is factory preset for two reasons. The first is to protect the instrument against high F noises, while the second is to enable you to see digital and clear signals. In fact, substations up to 735 kV produced a high-voltage electrical and electromagnetic induction, especially near lines with so-called live voltages. It's a resistive state between 30 and 2,400 ohms. If you see 400 kV, the half state indicates a resistive state between 30 ohms and 4,000 ohms. Depending on the circuit breaker, Zensol makes specific adjustments to suit the customer's needs. For example, settings from 30 ohms to 6,000 ohms are common, especially for instruments designed to test oil breakers. How do I activate a contact input using the fourth green button? Simply click on the fourth green button to show and activate or deactivate the contacts, which will be displayed in yellow-red. Yellow and red are associated with the colors of the battery clamps, which are yellow-red. It's also important to know the software number between 17 and 40 of the contact cables you're using. This makes it easy to visualize them on your graphical screen when the time comes to analyze them. This number is shown on the front panel of the instrument or on the contact displays. It's easy to change the name or color of a contact signal using the Property button. For example, on this slide, which shows 24 contacts, the plan designer has called the first contact in phase A, A1, the second A2 contact, the third A3 contact, and so on. Phase B contacts were named B1, B2, and so on. Thank you for watching this video.